Hello. So this is just a follow-up video to an episode of A Problem Squared with Matt Parker and Backhill. So they were trying to solve a problem to do with walking between bus or train stations and deciding which direction you should go. If you should go backwards or if you should go forwards based on your walking speed and the speed of the train. And they were a bit confused about why the math works. So I just wanted to clarify that. If you want to hear the full question, there's the podcast and links to the times below. So I just wanted to talk about my process of how I tried to figure it out. In the podcast, Matt Parker said that 1 minus the person's walking speed relative to the train, so like 17% the speed of the train, was a completely arbitrary or useless figure. But I recognize it as the relative speed of the train compared to the person. So it's a thing that comes up in special relativity sometimes, because with special relativity, when you add or subtract times, then and it's close to the speed of light, then it doesn't really add up, but otherwise it adds up. So if you take the person's frame of reference, think of them as not moving, then the train would be moving at 83% that's regular speed from ground level. So the thing I did was I just simplified the units a bit. So I made it so that the distance between the stations is 100 meters, and the train goes 100 meters a second, and the person goes 17 meters a second. So the train in 1 second will go to from station 1 to station 2, and the person walking will go 17 meters. So if you think of it as the train moving like instantly, so not the speeds I just said. So the train starts here, instantly gets here, then it wouldn't really matter which direction you go. So you start at 50%, you could walk that way or walk that way, it doesn't matter. But as the speed changes, then it matters more. So I was thinking of that special relativity thing where the train's going instantly. And the way I actually thought of it was thinking of a train being at station 1 and a different train being at station 2 at the same time. And then it wouldn't really matter so much because if you're only thinking of those two trains and not this train moving, then there's a train at each station. So it doesn't really matter. So it's like, yeah. So with the simplified times, then I tried to do it with easier numbers or easier percentages. So I picked easier numbers, having the person walk at 50% of the speed of the train. Then you can simulate the train moving. What you can do is you can have them start at 25% and have the train start at negative time behind. So they're at minus 50. And then in that same time, you're both going to reach station 1 at the same time. So in like half a second. Normally you can go, so if you go 50 meters a second, you can go 25 in half a second, and the train can go 50 in half a second. And then at 25, then you can go to half in half a second, there in 1 second, and there in a second half. And the train likewise can go there in half, there in 1 second, and then there in 1.5 seconds. So yeah, then it was just figuring out how to make it work with less nice numbers. And that was kind of tricky. So I wasn't really able to figure out the first day I worked on it on Monday that the podcast came out. So I slept on it and came back to it on Thursday, and then it was a bit more clear. And the way I figured it was working was that you have the middle 50% be like the starting point by default, and then you have the distance or the percentage expand from the middle in both directions, because the way it works is that in the time that the train can go 100%, then you can go 17%. So you don't just go this distance, you'd go the whole 17%. So as the train goes 100% of the way across, then you get 17% of the way. And then that's effectively having it so that the distance to a station with a train at it is the same either way. So here at time 0, then the distance to the station with a train at it is like 41% or whatever, 41.5. And then over here, as things moved along, then the distance is the same. So the key is thinking of it as starting at the 50% thing by default, and then the percentage expanding, or the distance walk expanding. And then I wanted to tie it back into my idea of the relative speeds. So what you can do is you can have the things starting the same, but then you have it so that space moves instead of the person walking. So it's like the world is flowing backwards, and then and then it's like the person was in the center the whole time, and then the whole world shifted back, and then that gap, that space, it was sort of just like moved to the side, and then space was almost like shortened or like moved so that at the start you have that distance. At the start you had this distance, then as time moved to station with the train at station 2, then it had that distance there. And right now, I'm not sure if that totally makes sense with the relative speed of the train. Oh yeah, and I think that the way it works with the relative speed or the world shifting backwards is that if the world shifts back, then it shifts back by this amount. So if you unshift it and keep the train in the same spot, then it would be at 83%. So in the shifted space, then it only moved 83% of the distance. So the speed is the relative speed in that case. I think that makes sense. So yeah, hopefully that clarifies things a bit.